Today's episode is sponsored by Datadog, a cloud-scale monitoring platform that unifies metrics, traces, logs, and more in a single pane of glass. Automatically alert on performance anomalies, easily build custom dashboards, and collaborate to resolve issues in real time. Try Datadog for yourself with a free 14-day trial. Hansel Minutes listeners will also receive a free t-shirt. Visit bit.ly.com/DatadogShirt. That's bitly.com/DatadogShirt to get started. Hi, this is Scott Hanselman. This is another episode of Hansel Minutes. Today I'm talking with Sara Beck. She's a machine learning solution principal at Slalom Build. How are you?
I'm doing well, Scott. How are you?
I am very well. I am out here teaching myself as much as I can about data science, but it's a little confusing. There's machine learning, there's deep learning, there's the data, there's the algorithm. Maybe you can start by helping me understand the difference between machine learning and deep learning, because sometimes I feel like the journalists and the tech writers just squish it all together.
Oh, I would love to. Machine learning is a general term for algorithms and data science that are optimizing something under a constraint. I know that those sound like some fairly technical mathy terms, and I'd be happy to break that down more in a minute. Deep learning refers to a specific area of machine learning that tends to deal with what we refer to as neural networks. And neural network type models are very important for computer vision and have made great strides in image processing and audio detection. General machine learning algorithms they can work on many more problems. Things that, like, for example, if you wanted to identify all of the cats in a picture, you might apply a deep learning algorithm to find all the cats, whereas a machine learning algorithm, others might be able to tell you, oh, this area of the picture has fur, and we think that the color of what we think is fur looks like a cat. So anyway, there's this little distinction between deep learning and neural network models and other algorithms where you can use the information to draw other conclusions or find out more about the problem you're trying to model. Does that make sense?
A little bit, but I want to get even clearer if you don't mind. It feels to me like deep learning architectures apply very often, or more often apply to fields like vision, speech, natural language, things that the brain does. Is that a fair statement?
I would say that is very fair. And in recent years, deep learning has led to huge advances in those areas. The reason deep learning techniques aren't as prevalently used all over the place has to do with the computational power required to train models on all of that data, and that deep learning models are also considered more of a black box model. There are a lot of data science problems where it's very important to be able to give an answer why a model is suggesting a certain output. With things like image processing, it's less important to know why an algorithm, in the example before with cats, decided there were many cats in the picture versus another algorithm where knowing why is important.
If it's a black box, if we're effectively, let's put this into simplistic terms, because I think a lot of the folks that are listening have written programs before, and they've written programs with lots of functions. And if I were to then have a function that is detect cat, and I write it programmatically, and I figure out some way in code with for loops and if statements to write a function that's detect cats, and then I turn that over to a deep learning system, something that's doing deep structured learning or hierarchical learning, and I train a model, and now detect cat is magic. It's literally like that Far Side cartoon we saw many years ago where someone's describing the complexity of a system, and then at some point they get into the algorithm, they go, and then a miracle happens, and then you continue on with the rest of the algorithm. We're really inserting an unknown into our thing and just trusting it.
In a sense, we are. I would say that neural network models are great at doing what they do because they are designed exactly the way our brains work in terms of when we look at a picture and can identify a cat, the nerves in our eyes get these light signals from the picture, and then it is sent to many layers of our neurons. But for the most part, maybe an optometrist or a neurologist could describe this process. I don't know why, when I'm looking at this picture, I think it would look like a cat. Yes, there's a lot of unknown, but there are still ways to test and validate that these models are being very reliable.
We've had folks on the show talk about like bias in machine learning and deep learning, and how if your data in is bad, then your function out might be bad, and it could identify a person as a cat or a bush or anything like that. Is the goal to be perfect, or is the goal to be as good as humans? What is the goal when designing something like this?
Well, I would say that really depends on the specific problem someone is trying to solve. In terms of maybe a biometrics case where someone is using deep learning to identify a fingerprint or an iris for security reasons, in those circumstances, you really do need to be perfect due to what might be at stake in terms of security. If the goal is just to tell if there's a living creature or person so that maybe a self-driving car doesn't hit it or something else, then it really doesn't matter whether we're 100% perfect in knowing this pixel is a dog or a cat or person.
Right. If I use something like Google Photos, which is consistently asking me questions about new questions, saying, "Oh, is this a picture of your wife? Is that a picture of your wife?" And every couple of times I'll open it, it'll ask me things, and I presume it is then training. I'm teaching it more about my family, so it figures out who's who. If it gets someone wrong, it's I guess the worst case scenario is it could offend me, but it's not going to be like life threatening. But false positives, if it was looking at an image and saying that someone has cancer, that could be hugely problematic.
Oh, it could. And those problems also exist even with like blood testing or when looking at other biological tests that a doctor might suggest for diagnosis.
Good point.
It's so that problem isn't very unique to deep learning. And I know that in all of those fields, there's always the best effort to reduce false positives without missing diagnoses, because neither case is very good. It'd be very stressful to find out a doctor thought you had cancer when you don't, and not to mention expensive.
But you bring up a really good point. It really gets to the hype of machine learning and deep learning, is that we I think we're being sold, the lay person, the community is being sold an idea that these are going to solve the really unsolvable problems, but that doesn't mean that they're going to be perfect. They really aren't. Like blood tests aren't perfect, and deep learning models are not perfect.
Oh, that's exactly correct. And I would say that depending on the nature of the problem someone's trying to solve, deep learning algorithms may not really be the best choice, just because with these neural network models, you do lose that visibility into what is leading to the result, or an inference or learning you could glean from a different type of algorithm. Like, for example, if a bank had a machine learning model to assess whether someone was creditworthy, it would be good to be able to tell a loan applicant why their application for credit was denied so that they might be able to do something about it, versus like a deep learning model would just say yes or no whether someone was creditworthy, and it would be a lot harder to prove there is no bias.
That's a good point. Certainly, if we had a deep learning model that was telling me that I was guilty or not, or why I was going to jail, or why I was arrested, there'd be huge opportunities to either directly or indirectly introduce bias and have no way to confirm. It's just simply a thumbs up or thumbs down, which is a fairly, well, it would be a plot for a pretty scary science fiction movie.
Oh, definitely. I don't know that I'd want to watch that one.
So when we think about these models and when you say that you describe them as a black box, we don't always know why. But if the use case is appropriate, then it's okay that it is a black box, you're saying?
Yes, and I would say that even outside of deep learning, it's really important to make sure that whatever algorithm being selected really matches the use case for like what that problem is trying to solve and also the data available to try to solve that problem. It's kind of this triangle of how those three components work together: the algorithm, the data, and the nature of the problem.
So that requires really significant thought in the all three parts of that. You could see where someone might potentially take a shortcut. Maybe their data isn't complete or thoughtful or enough, or maybe they just picked the default or some inappropriate algorithm. Any one of those legs is wrong and the stool falls over.
Correct. And that's actually a really big part that will lead to what I'll call statistical bias that is a little different than what we might describe as bias in terms of discrimination or unlawful bias. Often people don't do their due diligence exploring the data and understanding how the data was collected and these little nuances that if you knew the answer to all those questions, maybe you would choose a different algorithm or approach the problem in a different way.
This has really started in the last, would you say the last 10, 15 years? This is not, deep learning isn't something going back into the 50s, is it? I mean, like maybe the neural networks and the understanding of how we might do these things have been around for a long time. But this is the last 20, 30 years, wouldn't you say, has been the big rise of deep learning?
Well, I would say that the rise of deep learning is definitely more in the last decade, 20 years, and coinciding with the increase in computational power and the ability to collect more and more data. People were familiar with the, I guess, methodology behind deep learning in terms of neural networks. Actually, I believe way earlier than the 50s. It's just there wasn't a good way to try to build those types of models at scale.
Right. When I was reading up on this, I understand that people were thinking about kind of learning algorithms in the 60s and 70s. And then the term deep learning was introduced by a woman named Marina Dechter in 1986. But in the early 2010s, when the realization that a GPU would be a useful thing for not just graphics, but for expressing and solving these problems, that's where things really kind of kicked off, because we all have GPUs and they've just been shooting bad guys, and suddenly I can use them for something else.
That's exactly right. Major unlocks in image processing as a result to this computational power. Just the tide of video games kind of reminded me of that.
Yeah. The idea that I have a deep learning capable GPU that I've been just wasting on shooting bad guys is not lost on me. There's something about GPUs that cause them to be just so much more appropriate for deep learning systems than general purpose CPUs. Hey friends, Backlog is an all-in-one project and code management tool development teams have been waiting for. With project management, bug tracking, wikis, and Git rolled into one easy-to-use platform, Backlog provides the powerful features that development teams need under a clean UI that anyone can use. You can easily onboard your whole team and start working on tasks in minutes. Additional features like Gantt and burn-down charts make it easy to manage projects. Mobile apps keep your team connected, and simple pricing scales with you so you can stop worrying about per-user charges. Build your next project with Backlog. Get a 30-day obligation-free trial at backlog.com/HanselMinutes. That's backlog.com/HanselMinutes. So I've been looking into building these myself, and as I learn about this, I don't understand what regression models are as I'm trying to pick the right data and feed this into a model. What is a regression model?
Well, regression models are not what I would describe as a deep learning algorithm.
Mm-hmm.
Did you ever take a physics class in high school, or where
Sure.
you might like try to design or use your data to find the best fit line?
Yep, absolutely. Yeah, you have a bunch of like dots on a graph, and you kind of like pick a line that goes through them all for the most part.
Regression models follow that classic format where you're trying to find the best line, or it could be a shape instead of a straight line that describes the data. In the case where you like have a line where you might have y being, I don't know, maybe the money in your bank account and x being time, like there'd be coefficients on the variables like time. There are different ways to build these models so that you can, like in this example of money over time, predict something that is linear and like a continuous number. There are other ways to apply these same types of regression models to questions that have a yes no outcome, or others where the model is actually very nonlinear, like something like perhaps a cost model or different economic models. Regression models are a great way to get some inference about like what's causing the result of your problem, assuming that all of the assumptions the regression models make sense for that situation.
Okay, so let me see if I can understand that and phrase it differently, because I'm still trying to learn about this. So, if I want to understand the relationship between some variables, and in the simplest case, it's a bunch of dots heading in a general direction, and I'm drawing a line through it like a vector, and I could then, if it's a nice straight line, I can predict what's coming next, and that can make answering questions about that data pretty easy. But if it's something like the stock market, it looks like it's random. And I guess one could argue that it's not random, and there's just an infinite number of variables that feed into it. I'm hearing you say that if I feed the wrong variables in, I might try to draw correlation where there just simply isn't any.
That's definitely part of it. If you have attributes that aren't impactful for what you're trying to predict, you have a risk of making bad predictions leveraging those variables. Another part I wanted to touch on was it's not just what variables you use, it's also how those variables are transformed before they are even used in the regression. For example, maybe one of your variables for a regression that has to do with whether or not someone will be accepted into a university. Maybe one of those variables is a grade someone had in a class. If it's a really hard class and only 2 people had A's, that's going to lead different model results than if maybe you use the score of what someone had in the class, like 98 compared to 73 or C or A.
Right. So you're saying that there's context in any story, and you're basically trying, the data that you feed into this model is a story that you're trying to tell. And as you go and you say, hey, I got a 98 in this class, I'm amazing. That's a story, but it doesn't necessarily tell the full story if it turns out that the next person in the class got a 60 and everyone else flunked. And, you cheated.
Oh.
Suddenly the story has a lot more context.
Yes, and models will handle things like we just described differently depending on the nature of the algorithm, how many people, or how prevalent the different situations are that are being modeled. A lot of what I consider data science myself is building an empathy for the situation you're trying to model and the data so that you can really apply the best algorithm.
The other thing that's interesting is that these are situations that change, right? Like using the classroom example, classes and things that we take in college are different now, and they'll be different in 10 years, and they're different than they were 20 years ago. So you could describe a model that's amazing, but in 6 months, it turns out that that's not a good model. Are you going to be constantly revising models?
The constant revision of models does happen quite a lot in practice. I would say that there are maybe 2 major camps to model updating. One is perhaps you're building a beautiful model that works well for right now, and you implement that same model over and over again until time passes and your model has become stale because you're noticing maybe higher error than you were before. Another camp of machine learning models would be called online learning. Do you use any Internet of Things devices like a smartwatch, for example?
Oh my goodness. You asked the wrong person because I've got about 40 different Internet of Things. My house is the Internet of Crap. I have all the devices. So yes, the answer to that question is absolutely.
Well, myself, I'm an avid triathlete and I wear a smartwatch when I train. Often the estimation for how fast I'm going when I'm running, the type of model that's used to make those estimates would be in the class called online learning, where it's learning from the information you have right now based off of a few different measurements. So that's being updated continuously as time goes on. Like a smartwatch doesn't need a new model, it just needs new information to make sure I'm getting a great up-to-date running speed.
Right. So then using the example I had before of the Google Photos, the model is solid, but they just need more context about new photographs that are being taken. And they go, hey, I think these are the same person. Give me a little bit more information. And then the model improves.
Yes, I don't want to speak for Google because I don't work for them.
Of course. I'm thinking in the general sense.
In the case of deep learning models that are computer vision based, my best suspicion is that they have maybe a kind of a scheduled model retraining where now they have enough information, it's a few months later, let's retrain and deploy. Whereas deep learning image processing models can be very difficult to retrain very quickly. So you're more likely to see something scheduled or have periodic updates on more of a rigid cadence.
Okay. So if I'm having to do that, like how would I know that my model needs to be retrained regularly? And would I then kind of introduce, for lack of a better term, continuous integration and continuous deployment into my model so that I've got a model I use at my company and then we decide every quarter we'll go and retrain and redeploy?
In terms of using something like continuous integration for machine learning, that is very problem specific. I often see models retrained in practice in kind of two bigger situations. One is when there's now like an undesirable outcome in terms of error or something in a different process has happened where maybe it takes the model longer than it should, or an increase in maybe false positives. The other situation is when maybe the model needs to support a new feature or the nature of the data is going to change so much in the future that the old model will not be relevant. So a common strategy I've seen a lot of companies use in terms of when to promote a new model to production is to actually use A/B testing and see how a model is performing relative to the old trusty production model.
That's a very good point. If one is going to introduce revisions to their model, one should not just blindly deploy the newer one because it's newer. It may just well be worse. And unless you test, you won't ever know, which is a good reminder that whether it's machine learning or deep learning or just straight procedural programming, measure twice, cut once.
Definitely.
That is a really good point. Trying to figure out the integration point for these things, how the data scientist interacts with the development team and where the line kind of blurs is kind of a little bit fascinating to me. I know that you work on systems with large builders and other engineers, and usually I assume that does the data scientist sit with the developers and you all work hand in hand? You're a developer as well?
I would say that during the earlier stages of a project, I'm more likely to work with a data engineer or other data scientists. And towards final stages of a project, I'm more likely to work with a developer or software engineer to, build the API, make sure that everything is being well integrated.
And then towards the end, it runs on its own, and you're needed less so, and it's more of a keep it keep the lights on situation?
I would say so. I guess after you said that, one example of a past experience really popped to mind. I've built some digital fraud models in the past and to detect fraudulent transactions, and fraudsters never sleep. So in that sense, data scientists need to continually work to make sure that their models are preventing as much fraud as possible. In other circumstances, my job would be done, and maybe someone would call me for future support if something looks strange. But I know I've been saying this a lot. It really depends on the situation. Fraud would be a huge example of the work is never finished.
Well, and I think it's important that you are saying that a lot. And I don't think that that's something to apologize for, because what you're really describing is, if ever there were an industry where, quote unquote, it depends, it is machine learning and deep learning. And when you're training these models, I'm hearing you say that really a true understanding of the problem space is as important as anything. It is important in that three-legged stool that you were describing about the data, the algorithm, and the problem space. And to not think about that or not respect that understanding the problem space is important is to doom yourself to fail.
Oh, I could not agree more with what you just said. It's hearing someone else say it is like music for my ears.
That makes me feel like I understand that, that's why we do podcasts, right? Because we try to come to an understanding so that myself and the listener and the audience all go, okay, now we do understand it, because I can paraphrase it back to you, which makes me happy.
Great. Just because data science is between what I would say business and technology, I think it's really a creative job that requires a lot of empathy, trying to make something feasible for both the business user, the customer, and the technology engineering side, without asking questions and really diving deep into those problems. You're not going to be able to do a good job pleasing both groups of people.
Yeah, absolutely. You've got a lot of constraints to work within, and this is where the model is such a, for lack of a better word, a squishy thing. You can't really put your finger on it, and you can't really understand it. So you make sure that the things that you do understand are as clear as possible, so that the inputs, the three inputs that we've been describing, are put in. And if you come to new understanding and you understand it better, then you make sure that understanding is fed back into the model.
Of course. It's a very iterative process where maybe we explore the data, we build a model, and back when we gain more understanding, it just kind of cycles on an iteration until enough cycles have happened where it's ready to be deployed, or all the wisdom that can be gleaned is there.
Not to put you on the spot, but do you have a favorite book or a favorite starting point for people who are listening and they want to go and they want to do AI? I sometimes people I say to go to AI school, which is a thing that Microsoft offers. There's lots of different online tutorials and books. I'm curious what your favorite is, or a favorite author in the space.
This is probably going to reveal I'm a certain type of data scientist more than others. I enjoy the textbook Bayesian data analysis. I really like this book because the Bayesian school of thought helps people apply other wisdom from areas that they do know something about, and helps people integrate that prior knowledge into other models that then can update those opinions and prior knowledge. So philosophically, I enjoy that book for someone trying to learn. But I don't actually spend a lot of time reading data science or machine learning books. I'm more likely to read a tech article or perhaps a Medium post.
And I'm going to go ahead and get links from you or suggested reading. There's all kinds of great places online where people can learn, like edx.edu has great data science articles, Coursera, and others. So we'll have a link to that book and others in the show notes for this show.
That'll be great. I look forward to sending those along.
Fantastic. Thanks so much for chatting with me, Sara Beck. She's a machine learning solution principal at Slalom Build. And be sure to check out the show notes for all the different things that we talked about. This has been another episode of Hansel Minutes, and we'll see you again next week.